Here is my second DER of my grade 12 year, the CHUMP code clock encounter, a project consisting of two primary circuits and a CHUMP example code written in Chumpanese. The first circuit is a clock circuit in which both an astable and monostable mode can be toggled between using an SPDT slide switch. The second being a program counter used to toggle through the CHUMP's code and works using the clock signal represented through a binary LED display, both of which play vital roles in the soon-to-be-completed CHUMP 4-bit computer. The first portion of this project is the clock, a circuit in which the clock signal used to run the CHUMP is created and made up of two modes, astable and monostable. The astable mode, or in basic English, the automatic way, is when the clock pulses automatically and is built off of a 555 timer IC and a capacitor and can be manipulated using a 1 million ohm pot to lengthen or shorten the wavelengths. From there, the circuit can be debounced using a 104 capacitor to reduce noise within the pulses. Secondly comes the monostable mode, or once again in English, the manual mode, where pulses are created using a PBNO, or push button not open. This circuit must also be debounced and attached to a 555 timer IC and various capacitors to smooth out the signal, preventing the CHUMP from skipping over a code line. Thirdly, an SPDT slide switch is introduced, bridging the two circuits, creating one bistable circuit, which is also debounced using a third and final 555 paired with another 104 capacitor. The fourth and final subcircuit is the logic behind the clock, in which the previous three circuits are combined using logic gates to create the clock signal to drive the CHUMP 4-bit computer, with an addition of a new line, the halt line, one that, if wired high, stops the program. The logic on screen is one built and works straightforward. For example, the astable pulse is high, select is low, manual pulse is low, and halt is low. Using those conjunctions, the output would be low. Feel free to pause and solve it yourself using the logic gate on screen, or take my word for it. Ultimately, using the clock's four subcircuits, the CHUMP's clock is entirely constructed. The second and final portion of this build is the program counter, a circuit in which the clock signal is manipulated into counting in binary using the SN74 LS161AN IC. This binary counting IC counts in binary using one clock input to its four output pins, in this case visualized through green LEDs. Yet, once the load pin is wired low through a NAND gate, it uses inputs A to D, and those are the inputs outputted. This is explicitly not important in this build, will be in the future, as the NAND gate is used in the goto function within Chumpanese, and can be visualized using the rocker switches demonstration shown on screen. The third portion of this project is the Chumpanese code, in which I have created a basic 16-line code that solves 2 to the power of n, or better known as Pascal's triangle. Pascal's triangle is a triangular array of numbers in which those at the ends of the rows are 1, and each of the others is the sum of the nearest two numbers in the row above. To solve which, the user must input the value of Pascal's triangle they would like to solve. The code then first stores n's value into RAM address 0 using such values as necessary repetitions. Next, a value of 2 is loaded into the accumulator, as the equation to solve is 2 to the power of n, which is then stored to RAM, but this time into value 1. Next, the n value is found by reading RAM value 0, then loaded into the accumulator for further manipulation. As the first cycle begins, 1 is subtracted from the accumulator, then tested if it equals 0. If not, the value is once again stored into RAM address 0. Following such RAM address, 1 is read, then loaded into the accumulator, then added to itself to simulate a multiplication. Then, once again stored RAM address 1. Finally, the cycle is repeated until the if 0 command is true, of which the RAM value 1 is read and loaded into the accumulator, solving the equation. Note, due to the fact that there can only be 16 lines, n must be equal or greater than 1 to solve.